The protective shield of our planet decays and eventually fails. So do our satellites. First, communication satellites in the highest orbits go down. Next, astronauts in low Earth orbit can no longer contact their mission control center. And finally, hazardous, relentless cosmic rays start bombarding everything on Earth, causing havoc and devastation. Are these the terrifying consequences of the planet's magnetic field reversal we're going to face? Right now, as you're watching this video, Earth's north magnetic pole is extremely out of whack. It's so serious that scientists will have to update the global magnetic field model released a mere 4 years ago. Does it all mean that the magnetic pole of our planet will flip soon? Well, be patient, we'll figure it out a bit later. You see, the magnetic pole is moving quite erratically from the Canadian Arctic towards Siberia, and these movements are very unpredictable. But it's normal for the pole to be moving. There are long-term records from London and Paris that prove that the North Magnetic Pole moves randomly around the rotational North Pole over periods of several hundred years. But the most astonishing thing about its movement is that it's speeding up. Around the mid-1990s, the magnetic pole unexpectedly accelerated from a bit over 9 miles to 34 miles a year. And recently, the pole crossed the international dateline, moving toward the eastern hemisphere. The European Space Agency launched extremely accurate magnetic field satellites in 2013. Thanks to them, researchers have superb data they can use not only to make magnetic field maps, but also to update them every 6 to 12 months. That's how they were able to notice that the core field was weakening too. It might be a sign that the planet's magnetic field is about to flip. To understand this process better, we need to figure out how the core field works. Let's say we've got a bar magnet that runs through the center of our planet and has a north and a south pole. This magnet is incredibly strong, representing about 75% of the intensity of our planet's magnetic field at the surface. Our bar magnet is not only moving, but is also getting weaker, by about 7% every century. Admittedly, this bar isn't the perfect representation of the core field. It's more like electric currents generating Earth's magnetic field. Still, this model makes it easier to see what's happening to our planet now. The magnetic field of our planet plays an important role in protecting us from dangerous radiation and geomagnetic activity, which is the product of the interaction between the solar wind and Earth's magnetosphere. Earth's magnetic field also moves. Scientists have been studying and tracking the movement of the magnetic poles for hundreds of years. The historical motions of these poles indicates changes in the global geometry of the magnetic field of our planet, and they may point to the beginning of the field reversal too. That's what the flip between the north and south magnetic poles is sometimes called. You see, if the north magnetic pole moves a bit, it isn't a big deal. But a complete reversal might have a serious impact on the climate of our planet, as well as modern technology. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. So those scary events from the beginning of the video aren't likely to happen to us. The magnetosphere will continue protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current is negative charges called electrons moving through the metal. The current is what generates a magnetic field. Earth has a liquid iron core. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving through the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic radiation, which otherwise would be extremely dangerous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and the magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. But sometimes, the sun starts shedding gargantuan magnetized clouds of gas that can accelerate to incredible speeds. They're called coronal mass ejections, or CMEs. They're ejected from the sun over the course of several hours. CMEs usually look like giant twisted ropes and can occur spontaneously. Their frequency varies according to the 11-year-long solar cycle. For example, at a solar minimum, you can observe one ejection per day, and when the sun is in its most active phase, there might be 3 CMAs per day. Coronal mass ejections disrupt the calm flow of the solar wind and cause serious disturbances that can damage stuff both in space near Earth, like satellites, and on the planet's surface. If coronal mass ejections make it to Earth, their interaction with the magnetosphere generates geomagnetic storms. Those can trigger auroras, happening when a stream of energized particles hits the atmosphere and lights up. And then there are also solar flares. They develop more rapidly and with much more energy than coronal mass ejections. Solar flares often occur soon after coronal mass ejections. The most powerful volcanic eruptions pale in comparison to solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with temperatures reaching several million degrees Fahrenheit. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. A powerful solar storm can potentially cause a devastating global blackout on Earth. If not for the Earth's magnetosphere, the effects of the sun's activity would be much more devastating. Luckily, the magnetosphere deflects most of the solar material hurtling towards our planet from our star at a speed of over 1 million miles per hour. But even so, during space weather events, there's a lot of hazardous radiation near Earth. It can potentially harm astronauts and spacecraft. Plus, space weather can damage large conducting systems, for example, pipelines and power grids, by overloading currents running inside them. Scientists regularly map and track the overall orientation and shape of our planet's magnetic field. To do it, they use local measurements of the field's orientation and magnitude. That's why they've been able to conclude that the location of the North Magnetic Pole has moved by almost 600 miles since the first measurements were taken in 1831. The magnetic field of our planet reverses on a timescale varying between 100,000 to 1 million years. One can tell how often it happens by looking at volcanic rocks at the bottom of the ocean. They capture the orientation and strength of Earth's magnetic field at the time of their creation. So, dating those rocks gives us a good picture of how our planet's magnetic field has evolved over time. From a geological point of view, field reversals happen quite fast, but they are extremely slow from a human perspective. A complete reversal normally takes a couple of thousand years, but during this time, the orientation of the magnetosphere may shift, exposing more of Earth to cosmic radiation. Such events tend to change the concentration of ozone in the atmosphere. In any case, scientists can't say for sure when the next field reversal will happen, but they keep mapping and tracking the movement of our planet's magnetic north. By the way, the Earth isn't the only planet with a magnetic field. Gas giants, like Jupiter, also have a conducting metallic hydrogen layer that generates their magnetic fields. Jupiter's internal magnetic field prevents the solar wind from interacting directly with the planet's atmosphere. So, what would it look like to go around Earth at the speed of light? Well, I'm guessing pretty quickly, but let's get to the details. Traveling around Earth at the speed of light would be an astonishing sight to behold. If we could magically achieve such a feat, here's what it would look like. As you kicked off your speedy journey, everything around you would get blurred. The landscape would transform into a streak of dazzling lights, like a cosmic fireworks show on fast forward. The world would appear distorted, with buildings and landmarks merging into streaks of brilliance as you zip past them. The familiar features of cities would become blur colors, blending together in a mesmerizing display. Day and night would blend seamlessly, since Earth's rotation would become an indistinguishable whirlwind. However, keep in mind that at the speed of light, time itself would behave strangely. To you, the journey might feel instantaneous, but when you return, you'll find that much more time has passed for everyone else. It's like taking a lightning-fast trip while the rest of the world ages. Sadly, achieving the speed of light is currently beyond our technological capabilities. Okay, but do you know what the speed of light actually is? In the vast expanse of empty space, the velocity at which light travels is an astonishingly precise figure. This translates to approximately 186,000 miles per second, a universally recognized constant notated as c, or the speed of light. Drawing from the revolutionary principles of physicist Albert Einstein's theory of special relativity, which forms the bedrock of modern physics, we come to a remarkable realization: nothing in the entire universe can surpass the velocity of light. According to this theory, as an object comes close to the speed of light, its mass spirals toward infinity. Consequently, the speed of light operates as an indisputable cosmic speed limit, casting its influence over the entirety of the universe. Such is the fixity of light's rapidity, yes, I have a thesaurus, that it finds purpose in defining internationally accepted units of measurement, like the meter and mile. The United States National Institute of Standards and Technology reveals that the speed of light even contributes to the definition of the kilogram and the temperature unit known as the Kelvin. Now, let's talk about the speed of dark. Darkness, the elusive counterpart of light, seemingly travels at the speed of light itself. In reality, darkness doesn't exist as a distinct physical entity, but is rather the absence of light. Whenever you block out a substantial portion of light, like when you cup your hands together, darkness fills the void. When discussing speeds, we can think of darkness as what emerges once the light ceases to illuminate, and it appears to move at the speed of light. Still with me? Yeah, my brain is starting to ooze out my ears too. Anyway, let's take a journey to distant space, far away from any light sources, such as the radiant sun. Imagine having a light bulb attached to the nose of your spaceship, emitting its luminosity in all directions through space at the speed of light. Now, if you momentarily turn off the light bulb and then turn it back on, a fascinating phenomenon occurs. Light continues to travel outward in all directions from before you dim the bulb, and subsequent light beams follow after you restore its glow. However, amidst these expanding spheres of light, an intriguing region emerges. It's the space in between there was no light because none was generated during the brief period when the bulb was off. So, in this cosmic spectacle, darkness appears to join the journey alongside light, seemingly chasing it at the speed of light. It reminds us that even in the absence of light, there is an enchanting interplay between shadows and illumination, each playing its unique role in the vast tapestry of the universe. Whoa, something doesn't feel right. Everything seems shaky. It's definitely not an earthquake, and it's actually getting worse. The clouds seem to move quicker than usual, and the animals are going into a frenzy. The news anchor pops up on the TV in an alarmed tone and says, "Good morning. We're sorry to interrupt your program. Scientists have just discovered that the Earth's rotation has been fluctuating at an unusual rate. A group of specialists believe that the Earth is increasing its rotation with every second, and they don't know why." Even if the Earth increased its speed by 1 mile per hour, the day would only get shorter by a minute and a half or so. We wouldn't really feel it, and you could go on like nothing is happening. But as the Earth spins faster, our bodies, which are adjusted to a 24-hour timing, will have a hard time trying to cope with it. If you live by the equator, that means the rotation of the Earth is going quicker than at the North and South Pole. The area by the equator needs more time in order to complete its full rotation from the starting point. You'll experience more rain than usual. The Earth's rotation keeps the weather consistent and balanced so that nothing abnormal happens. But because the Earth is moving so fast, the weather is acting up. We'll start to see more storms and more cozy days inside, sipping on hot cocoa. Even though it seems weird, everyone can go about their day. But if the Earth picked up some speed and moved at 150 feet per second, the day would be reduced to only 22 hours. It kinda makes you feel jet-lagged 24/7. Every business works with the 24 hours a day schedule, so taking away even 2 hours can have catastrophic effects on the world economy. The whole calendar will have to change and adjust to the new timing. Clock designs will change with the new midnight, replaced with 10 o'clock. And with each week, the hours will shorten, so there will be no proper way of telling time except by sunsets and sunrises. The weather will continue to get worse and worse, feeling like the rain will never stop. The animals that rely on weather patterns won't know how to function, and mass migrations will occur from almost all species of animals. Flocks of birds will be flying everywhere and reach places they normally won't go to, affecting the whole food chain and ecology. Woods, jungles, and other places where animals roam are kept in proper balance when unaffected by humans. If it constantly rains in certain areas, then floods will force animals to move to other territories and compete with the predators in the area. If the Earth picked up speed every day, then standing on a scale in the Arctic would tell you weigh 180 pounds. But around the equator, you might weigh about 179 pounds. That's because of the extra force opposing gravity in that area. With the Earth spinning faster, all airlines around the world stop, since the radar systems have gone haywire and the weather is too dangerous to fly. Everyone has to get around by car. Satellites are positioned in such a way that it's crucial they remain where they are in order to bounce signals to us. Because of what's happening, Wi-Fi and TV signals can't go through. Communications around the world will end up short and slow, and eventually we'll have a total communication blackout. Ships will cease to operate, and global trading will collapse, adding extra damage to the already failing world economy. Winds will get stronger and faster than usual, which means temperatures will change. Storms like hurricanes will be stronger than ever and have more energy for destruction. And still, at 100 miles per hour, the equator will now be swallowed up in the water. The Amazon basin and small islands will now completely submerge in water by around 50 feet. Most of the plant life will be endangered, especially by the equator. With woods threatened by floods, more animal environments will be in jeopardy. The trees and plants won't survive so much flooding. If the Earth rotated so fast that the hours would now be reduced to 15, then we'd probably feel like we're always on a jet plane going through turbulence. It would be impossible to sleep if the Earth kept picking up speed every second of the day. So days would be around 7 hours long as well as nights. The whole world would be flooded, except for the highest points and the tallest mountains. If that happens, humans will most likely end up there clinging to the last remaining clear patches of land. Most of the animal life will be extinct as well. And as the Earth is spinning faster and faster, the crust will lose its durability, allowing more frequent and stronger earthquakes to happen. Volcanoes will erupt all over, even if they're submerged in water. It'll go on like this for quite a while. Many major natural disasters like earthquakes, tsunamis, volcanoes, and even melting ice sheets have sped up the speed of the Earth by milliseconds. So, with the Earth's continuing speed increasing, these natural disasters will make the planet go even faster. Even if it's just for milliseconds, it's enough to have major consequences. The Earth is now spinning at 1,000 miles per hour, and as you're sitting with the rest of the survivors, you feel yourself levitating slightly. you'll see tiny pebbles and rocks floating inches from the ground. The clouds above you are passing like shooting stars. The air is thick with moisture, since water is rising to the top, forming thick clouds ready to pour. But since gravity is weaker, some of the rain is suspended in the air. Many small objects will be floating around as if you were in space. The days and nights won't be longer than a few hours. At this point, the whole world will be flooded, and the crust will be 80% gone. If it goes on any longer, there won't be any living things around, probably except for microscopic creatures that can withstand extreme and harsh conditions. The Earth would need to spin at approximately 17,600 miles per hour to cancel out the gravity for things to start floating around. At this point, all the water in the ocean will rise and look like reverse rain. The large mountain rocks will separate from the bedrock and levitate above the ground, looking like little planets in space. The Earth is now spinning 17 times faster than usual, which makes one full rotation around its axis only 84 minutes instead of 24 hours. If you manage to stay that long, then you'll literally see the days and nights go by in an instant. You'll also be floating aimlessly in the sky, bumping into rocks and other surfaces. You won't recognize anything anymore. The Earth's crust is ripping apart, exposing the magma underneath. So landing on the ground isn't an option. You'll see outer space as you go higher and higher. You won't know how fast you're going, but all you know is that you're probably the only human left in this spinning world. The Earth will eventually spin so fast that the rest of the layers will start to peel off, exposing the Earth's interior. It'll start to squeeze itself from the core until it becomes similar to a pancake. Nothing can survive at this point. So much heat will be produced from the core that the planet will heat up like a microwave. All the water will disappear, and it'll look like a red dot in the solar system. And once it starts to approach the speed of light, time will freeze. The rocks and floating elements won't move and will eventually be distorted. And with enough effort, the Earth will eventually turn into a black hole. Of course, nothing like this will ever happen. According to scientists, Earth will most likely slow down in rotation. Ever since the Moon came into the picture, the Earth has been slowing down by around 4 miles per hour every 10 million years or so. That's because of the Moon's gravitational pull on our little blue planet. It'll most likely go on that way. So hey, what's your hurry? You're in the middle of the Sahara. You see a huge awning with a red target pattern. Its surface is so hot you could fry food on it. A drop of water is to hit the center of this target at the speed of light. Theoretically and technically, this experiment is impossible to conduct. But if it happens, then mysterious nothing awaits us. And each version of this nothing will be different. So we'll do 3 drops. Option 1. It's better to do it from a great height or space. You take off on a jetpack into the stratosphere. You have a bottle of water in your hand. You pour out 1 drop. Let's say it starts accelerating itself. In this case, even at a low speed, a drop of water will burn up in the protective layers of the atmosphere. In less than a second, the drop will turn to vapor. Let's say our planet had no such protection as the atmosphere. The air resistance would still get rid of the drop. The drop is flying down at a tremendous speed. The cold wind turns it into an icicle. The greater the drop velocity is, the stronger the air resistance is. The drop is moving faster and faster, soon reaching the speed of sound. Then, it just smashes into thousands of small particles. Under such conditions, the drop will never be able to reach the Earth at the speed of light. Nothing happens because nothing gets to the target. The next attempt involves changing the drop. Oxygen, carbon dioxide, ozone, and other gases in the atmosphere destroy any falling object. But what if the drop didn't meet all these obstacles? You change the internal structure of water chemically. So, you put your jetpack on again and grab a bottle of water. At the height of the Earth's orbit, you open it and pour out 1 drop. It accelerates and there's no resistance. It passes through the hottest layers of the atmosphere, but doesn't burn, passing the freezing temperature, but doesn't freeze up. It flies to the ground, developing the speed of light, and crashes again. But nothing happens. The drop got the properties of a light particle, a photon. It's only under such condition that it might develop the speed we need. No object with mass, be it a car, a house, a tree, an ant, a single air, a grain of sand, or a molecule, can reach the speed of light. Only light particles are capable of it since they don't have mass. An intangible drop falls into the center of the target, and again, nothing happens. The third option. Scientists found a way to accelerate a drop to the required speed. They also have to change the molecular composition of water, making it more resistant to high and low temperatures. To make the drop reach the speed of light without any damage, you need to place it in a perfect vacuum. No air resistance, no protective layers of the atmosphere. We leave only space and the water. For this purpose, scientists need to build a long pipe. In the center of the Sahara, around the same target, people create a scientific center. From here, the pipe should go up. Its height is approximately the distance to the International Space Station. That's 254 miles, which is about the height of 50 Everest mountains. You can't connect to the ISS itself as it's moving all the time. It revolves around the Earth, completing one revolution in 90 minutes. That's why astrophysicists and engineers should build a small station designed for one person. And this station should move parallel to a single point on the ground. The vacuum tube is made of solid stainless materials so that rain and high temperature couldn't destroy it. Inside, it's an alloy of titanium and graphene, the most durable metal on Earth. The pipe is built horizontally. Then, with the help of several helicopters and cables, it's placed in an upright position and attached to a small space station. The pipe is equipped with small pumps that pump the air out and block its flow inside. The water drop shouldn't touch the walls, so there's a special layer of gravity plates. They push the water away from the pipe's surface, using the power of magnetism and sound waves. You put on a jetpack and fly to the station with a bottle of upgraded durable water. Your hands are shaking with excitement. Your breathing sounds loud in the spacesuit. You open the bottle, tilt it slightly, and pour one drop into a special box. Inside this container, the drop gets charged with the energy needed to develop the speed of light. Now it's ready for the journey. You look at the box, close your eyes, and press the start button. The drop flies into the pipe at a great speed. From the powerful blast wave, the entire station is thrown to the side. The drop accelerates, and at this point, the pipe made of the strongest metals on Earth begins to melt like ice cream. There's so much energy in the water now that it would be enough to provide electricity to a small city. And now the drop reaches the speed of light, which is 186,000 miles per second. The pipe turns to dust. It doesn't matter whether the drop hits the ground or not, because there will be nothing. Literally all material objects, cars, houses, fields, oceans, computers, planes, ships, flowers, trees, should I go on, will disappear. Intangible things, such as gas, air, radio waves, electromagnetic radiation, billions of terabytes of digital information, all this will also be gone. Boy, are you in trouble. Any sound, shouting, music, the phone ringing, will be impossible to create and hear. The light will disappear, and then there will be complete darkness. But let's rewind time and see exactly what happened right now. It won't work though, because there's no time either. Imagine time as a stormy river that flows rapidly in one direction. Then this river falls into an endless pit and disappears completely. All this happened because a drop of water crashed into our planet at the speed of light. As soon as a drop begins to approach the needed speed, it loses its properties of water. It's now the most powerful and heaviest object in the universe. The energy that comes from it destroys everything for hundreds of thousands of miles. Concrete, ground, rocks, etc., 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 and on and on and on. Everything disappears. In the first second, it all gets shattered into millions of tiny pieces. Then these pieces are torn apart into millions of even smaller particles. The molecules burn up. Imagine a paper map of the world. If you wet it and tear it, it will turn into wet paper scraps. If you burn it, then part of the map will turn to ashes, and the other part will simply fly into the air in the form of smoke. The map will remain, but it will never look the same. But if you destroy the map's molecules, it's safe to say that the map never existed. There's no trace of its existence. The same thing happens to our planet. The energy coming from a drop of water makes the Earth never exist in space. And now the drop exceeds the speed of light. A black hole starts evolving. It expands and absorbs all the space debris. Then the Moon. Soon it will be the turn of Mars and all the other planets in our solar system. The black hole expands and increases the force of gravity inside it. Together with our planet, it absorbs light. It's getting closer and closer to the Sun. Our star splits into strips of light as if it had passed through a huge cosmic shredder. The sun explodes and spits out an impossible amount of energy. It's believed that black holes appear after the explosion of stars. Right now, all the solar energy is being absorbed by our black hole. It's getting pitch black. The light from distant stars falls directly into the supermassive infinity. Meteorites flying within a radius of hundreds of thousands of miles around are also devoured into the unknown. There are many black holes in space, but only one of them was created by a small drop of water. The higher the speed of any object, the heavier it gets. Mass is the amount of energy that an object has. When water molecules reach the speed of light, their mass begins to grow, and there are no limits to this. It becomes infinite. An infinite mass forms a black hole. It absorbs everything, and nobody knows what's inside the black hole. All that remains is darkness and the unimaginable force of gravity. So, I'm guessing here that we probably should not be doing this experiment, should we? How about we make a baking soda volcano instead?
The speed of light is the fastest thing in our universe. It travels across space, passing through Mercury and Venus to reach us, and it's slowing down. No need to panic though. The sun is getting weaker, but we won't see the effects of it for another billion years. In the vacuum of space, the speed of light is around 186,280 miles per second. Any slower than that, and humans would see the changes firsthand. There would be some awesome effects, like colors changing and the brightness of objects fading. We'd also notice some differences in everyday objects, their length and shape. Scientists created a simulation to see what would happen if the speed of light was slower. In a vacuum, the speed of light can't change, but if light passes through different materials and objects, it alters the way we perceive things. Light acts as a wave and a particle, meaning that it's a wavelength. The color and frequency are determined by the distance from crest to crest in the wave. It behaves similar to sound with the Doppler effect. Imagine you're standing in the middle of a busy highway and a honking car speeds through. Wow, that was loud. You can hear that whoosh-like sound of the horn because the moving object produces the sound while you're stationary. The frequency and pitch seem to change, but it's just the sound reaching your ear faster than it would if you and the car were both stationary. Light behaves similarly. The wavelengths change if the speed changes. Moving toward a light source and making the wavelength shorter will shift the color to a blue and violet hue. Moving away from the light source, and you'll get something more reddish. So if the speed of light slowed down to walking speed, we'd notice the colors changing when we approach an illuminated object. At the same time, the color would change around us and behind us. If you walk sideways, the colors you're walking toward would become bluer, and everything in the distance would become red. This information is useful to astronomers who are studying objects in space. If they're blue shifted, that means the object is moving towards us. And if it's red shifted, then it's going in the opposite direction. In fact, everything in the universe is red shifted, proving that the universe is expanding and getting further away from us. The slower it gets, the brighter it becomes. That's because the photons become more present for us to see. At this rate, we can see invisible light and increased intensity. You won't notice that effect much if you're standing still, but because of the Doppler effect, moving towards an object will have different colors and different light intensities. Another phenomenon we'd experience is time dilation. It's when you move at a similar speed as light and time decreases relative to someone who isn't. Space and time are relative. So if you're sitting at your desk wasting hours away, yeah, sounds familiar, doesn't it? All your movement will go through time and not through space. You're stationary, but you're still technically moving forward in time, slowly aging. The faster you move through space, the slower your movement through time will be. If you move at the same speed as light, then all your movement will be through space and not through time. To notice that, you'd need another person to watch you. You're not in a time machine. You're both on Earth, experiencing the same time flow. To you, experiencing this firsthand makes it feel like you're going faster, because you're getting a lot more movement in space in a given time. The closer you get to the speed of light, the smaller you become. Well, not really, but it depends on who's watching. If you're the one traveling at such a speed, an object nearby will seem small. Just as someone who's watching you travel at the speed of light will think that you're smaller than you actually are. The simulation that the MIT scientists conducted showed that if the speed of light drops, everything will become stretched out like a pancake. If you see mountains in the distance and then run at the speed of light, they will appear further away. Objects will become distorted, and it will feel like you're getting to a certain place faster because time has slowed down for you. If you're standing completely still and someone standing on your left-hand side throws a cube-shaped object over to your right-hand side, then naturally, you'll see one side of it unless it flips around. But in this new reality, you'll get to see the front side wrapping around the visible side you're seeing. If you're moving at the same speed as light in an infinite space, everything will be stretched out as you reach infinite speeds. In a world where people can walk at the same speed as light, we'll perceive nothing as normal. We'll have to get used to the way we see objects. Every movement we make will result in drastic shifts of colors. Even turning your head to look at something will feel weird. Let's say you're in a supermarket buying groceries, and you walk from aisle to aisle. The milk at the end of the counter will look like it's really close to you. But when you approach it, you'll start to feel like it's getting further away from you. The milk will also look a bit red. As soon as you get closer to it, it will shift to blue. If someone is passing through with a shopping cart, you'll see it as a sort of 3D model of a shopping cart. The color will shift as it gets further away from you. It will appear far away, but it's right in front of you. In fact, we don't really know the actual speed of light. Physicists gave it roughly 186,280 miles per second, but that constant is just for them to calculate other scientific stuff so we can understand it better. The problem is that we can only measure light with light beams and mirrors. But it's not like all we have to do is point a light beam at a mirror and measure its original path and its reflected path. Einstein's theory of relativity states that the original path of light moving from the source to the mirror may not be the same speed as the reflected light from the mirror back to the source. Hypothetically, if it takes light 10 seconds to travel from the source to the mirror and then back to the source, then we can conclude that each trip takes 5 seconds. But Einstein's theory is that it could take 9 seconds for light to travel from the source to the mirror and only 1 second from the mirror back to the source, or vice versa, or maybe completely different numbers altogether. That's why it's so difficult to measure light. A breakthrough came out for scientists when they managed to slow down the speed of light to 0 without losing its brightness. They did this by using ultra-cold atom clouds made with photonic crystals. These crystals are materials punctured with billions of tiny holes where light can refract. But what if we lived in a world where light stopped halfway? You'd wake up one morning and feel like it's twilight. You'd open the curtains and see that many car lights are on, but aren't so bright. You turn on the lights in your room, but feel like the bulb is tapping out. You replace it with another one, but it doesn't do the trick. You turn on the lights everywhere in your house, but it's all just giving weak light. You're confused and try to check if there's a problem with the electricity in your house, but it seems to be working well. You check on your neighbors, and they also have the same problems. Even experts in the field can't understand what's going on. Hours pass, and it's all the same. All the light in the world seems to have frozen halfway. Your phone is low on brightness, even though you bumped it up to maximum. Everything is getting darker. You learn from the news that it's a global problem. Light is slowly diminishing, and soon there won't be any of it in the world. You decide to wait it out while everyone else is panicking.
Cold and seemingly infinite expanses of the Arctic. The white of the snow is blinding. In this vast and empty space, there's a dark dot. Getting closer, it turns out to be a small research station. One door and one window. An old antenna on the roof wobbles from the strong winds. You're sitting inside this hut in warm clothes, drinking hot tea. An electric generator hums under the table. It's connected to a TV and game console. You take the gamepad and select the video game you want to download. It's about 650 gigabytes. It seems in such a place it will download over several centuries. But you press the button and the game is downloaded on the console in less than a second. Welcome to the world with the fastest and most accessible internet. The internet already works at the speed of light. Phones use a specific frequency of radio waves that travel at the speed of light. You're watching this video using the internet at the speed of light. Most of the data is transmitted through a copper wire or fiber optic cable. This happens so fast that we won't notice the difference whether it's transmitted at the speed of light or not. Wi-Fi also uses radio frequencies to transmit signals between devices. The fact is that the speed of the internet is not about how fast a file travels from one device to another. It's about how much data is transmitted over a certain time. So, let's imagine that data of any size can be loaded at the speed of light. 300 gigabytes of several movies in 8K, 400 gigabytes of a video game with ultra-realistic graphics, 1 terabyte of a project for a graphics editing application, and all of this is downloaded to your device in 1/100th of a second. The internet is a connection between computers. For everything to work correctly, the computers connect to a router. This thing works as a controller. It makes sure that the message from one computer reaches the other without any confusion. When there are too many computers, you need more routers that connect to other routers. You can scale this network indefinitely. To connect millions of houses to the network, developers can use telephone cables. To make this complex system stable, it's served by internet service providers. They're companies that we pay money to access the internet. In simple terms, all information from the internet is transmitted via a cable directly to the Wi-Fi router. It uses radio waves to wirelessly transmit data to a computer or phone. Your devices are also equipped with an antenna that can catch and transmit signals via radio waves. The speed of the internet slows down when it goes through different routers, receivers, and other technical hurdles. The cable may be damaged. Providers limit the speed intentionally and increase it when you pay more money. Also, the speed of the internet is affected by the number of users connected to the same network. It's like a broad highway with a traffic jam. The more cars there are driving on it, the slower they move. Just like that, your data is loaded onto your devices. To spread the internet at the speed of light everywhere, developers need to improve cables data passes through. The number of networks and routers should be increased. The jammed highway will become even broader, and cars will be able to drive at full speed. Providers should remove all restrictions as well. Every mobile device and computer should have a high-frequency antenna that catches signals from an ultra-fast router. Several huge routers are located all over the planet. They look like enormous boxes without windows and with giant antennas on their roofs. Deep underground, thick cables providing ultra-fast data transmission are connected to these boxes. As soon as the signal from the cable enters the box, it broadcasts to space via radio waves. Thousands of satellites hover over the planet and intercept these waves to spread them throughout the world. So, anytime and anywhere, you have access to the internet that's working at the speed of light. Movies and video games are created several times faster. A lot of time is spent trying to transfer a terabyte of data with graphics from one computer to another, which is located in another country. Now, with Super Internet, developers get any amount of data in an instant. Flash drives and hard drives are no longer needed in the world. Everything is kept in cloud storage. From there, you can download any file to your computer thousands of times faster than if you downloaded it via USB. Companies that provide cloud storage services are becoming the richest in the world. You have access to the internet in the elevator and the subway, in the mines deep underground, and among the hot sands of the Sahara. The phones are released without internal memory and with an incredibly cool camera. You can record an infinite number of videos with 16K quality and not think about where to store them. You can do color correction, develop games, or edit your videos all on your phone. You don't need powerful processors for such operations. Everything works with the internet. You remotely connect to a powerful computer and work from anywhere. That's why the market for expensive computers has collapsed. Nobody wants to spend money on a cool graphics card because a new one will be released in a year. It's much easier to connect to the computer where it's already installed. Even in our time, such companies already exist in great numbers. You can play a new video game on top of settings on your old computer or phone if your internet connection is fast enough. Super Internet creates a perfect climate for the rapid development of modern technologies. Virtual reality lenses, for example. On an airplane, in a submarine, in the desert, you can watch the highest quality movies in 360 or play games with augmented reality. Special effects and graphics in such games become indistinguishable from reality. Artificial intelligence can process data from all over the world simultaneously, in seconds. Thanks to this, people make discoveries in the field of medicine and genetic engineering. Scientists are developing a machine that can upload the human mind on the internet and download it back. Each user's cloud storage accumulates so much digital garbage that people hire special companies to clean up terabytes of useless data. A huge amount of energy is consumed. It provokes an increase in the price of electricity. To save money, people build small wind farms in their backyards to generate electricity. Many people make tunnels to get to underground rivers. Using special equipment and a powerful water flow, you can create a home hydroelectric power plant. The roofs of most houses are covered with solar panels. The internet is becoming as familiar to the world as the air. There's no longer a place where you can't connect to the web. Some vloggers put a phone in a box made of refractory metals and threw it into the mouth of a raging volcano. Even then, the connection wasn't broken until the phone melted. In a few years, the data on the internet as a whole increases thousands of times. Billions of petabytes must be stored somewhere. Developers around the world build data centers to support cloud storage. They appear underwater, underground, in the mountains, and even in forests. Scientists understand there won't be enough space for such data storage in the future. In addition, all centers emit strong radiation, which is bad for humans and the Earth's atmosphere. Therefore, the world's IT companies unite to create a giant data storage server in space. They build such a station in the orbit of our planet. Developers install special equipment there to ensure the operation of cloud storage. Every year, the station grows in size. It receives energy from solar panels. After a few decades, the data center becomes a cube half the size of Earth. You can look out the window and see its outline in the blue sky, better than the moon. At night, millions of light bulbs glow on it. An enormous area on the moon is covered with solar batteries to provide the cube with additional energy. Now it looks like a disco ball. Humans colonize Mars and take the super internet there. Now you can make a high-quality video call to a friend who is on the red planet. Rikat structure is a giant formation in the Sahara that looks exactly like a giant bullseye. It's so wide that you can see it from space. Even the CIA got interested in it. In 1965, they planned a flyover looking for geomagnetic anomalies. The findings are still classified. Perhaps the theories are true, and this place is truly the lost city of Atlantis. Now, Atlantis supposedly sank beneath the waves, but recent discoveries are pointing us in a different direction. This is an ancient story that goes far back in time, and Plato was the first to mention it. The place had loads of greenery and a curious structure: 3 concentric circles of land surrounding 2 circles of water. 2 key quotes from Plato's writing suggest that Atlantis might not have been a typical island in the middle of the ocean. Plus, Atlantis had a major influence from Africa and Europe, challenging the idea of it being in the Atlantic. It turns out that the Eye of the Sahara and Atlantis look alike. When astronauts saw the Eye of Sahara from above, they initially suspected a meteorite impact crater, but the rings of the structure matched the layout described of Atlantis. More importantly, the Sahara wasn't always a desert. It turned from a tropical region into a desert around 11,000 years ago. Researchers found evidence of a massive river called the Tamaracet that could have sustained a community. This river flowed toward the Rikat structure, aligning with Plato's description. The Trans-Saharan Seaway ran through the Sahara 50 to 100 million years ago. The sea allegedly destroyed Atlantis around 11,500 years ago, likely due to a rapid rise in sea level caused by the end of the Ice Age. NASA's worldview imagery shows patterns consistent with this theory. Those concentric rings might be a key to unlocking the secrets of our planet's evolution over millions of years. They're shaped by erosion on resilient rock layers, creating a spooky pattern of ridges and troughs. The central peak stands proud at 1,300 feet. The central part has undergone a significant erosion makeover, revealing a circular structure with a raised peak. Unlike impact craters, the Eye of the Sahara flaunts a striking balance and symmetry. Some say it results from rock uplift, sculpted by wind and water. Others think it's an ancient anticline, eroded to reveal its concentric glory. Then there's a salt diapir theory, suggesting that salt's buoyancy sculpted this beauty. Dating techniques have proved that it formed 541 to 252 million years ago, give or take a million or two. Ancient tools are scattered around the outer rings of the structure near riverbeds. Some older stone tools have also been spotted in the same areas. And still, even though some spear points from the Neolithic period have been found, there aren't many signs that people were living there back then. The area seems to have been used for short-term activities like hunting and making tools. There are other unearthly mysteries that haunt our world. One such enigma is in Norway, the ominous Hessdalen light phenomenon, also known as the Valley of Lights, leaves scientists confused. This valley is 10 miles wide. It's quite isolated, but a peculiar blue box sits high on the hillside, equipped with cameras scanning the valley. The unsettling saga began in the 1980s, when the night sky over Hessdalen erupted with burning fireballs, a recurring spectacle that sent shivers down the spines of those who witnessed it. This wasn't a fleeting occurrence, rather it became a regular thing. Terrified locals reported encounters with these unexplained luminous phenomena, some of which happened near their homes. Unease spread like wildfire. At its peak, there were about 20 sightings every week. The phenomenon made its way into newspapers, magazines, and media worldwide. Soon, people flocked to the valley, hoping to see the lights themselves. In 1984, experts joined the fray, armed with sophisticated instruments like magnetometers, radiometers, and other ometers. What they encountered was mind-bending, lights that defied explanation. Some moved at a leisurely pace, while others raced through the sky at an astonishing 19,000 miles per hour. People tried to explain these lights: airplanes, distant reflections, ball lightning, satellites, planets, meteors. But the speed and how these lights danced ruled out all those theories. We're slowly approaching another mysterious place. This is the greatest subglacial lake among Antarctica's 675 known lakes. It can easily hide unknown life forms. This lake is beneath the East Antarctic ice sheet. Dive about 2.5 miles under the ice, and there you'll see Lake Vostok, located at 1,600 feet below sea level. This lake is 155 miles long and 31 miles wide at its broadest point. With an average depth of 1,400 feet, it's also the world's sixth largest by volume. It's like an underwater city with lofty pillars and deep basins. The secret lake was discovered in 1993, yet it had been waiting to be found down there for over 2,000 years, collecting ancient secrets. In 2012, scientists drilled through the ice, creating the longest ice core ever. They pierced the ice all the way to the lake's surface. The year 2013 brought an unexpected twist when the tranquil waters erupted during the extraction of an ice core, mixing with drilling fluids. Then they got a pristine water sample in 2015. Some believe there might be previously unknown life forms down there, since it's a fossil water reserve that's been untouched for millions of years. That could be a lot like those speculated ice-covered oceans on moons like Europa and Enceladus. It all started with a theory in the 19th century, suggesting fresh water lurking under Antarctic ice sheets. Then, in 1955, seismic soundings hinted at a subglacial lake, and by the 90s, satellite data confirmed Lake Vostok's existence. Now, Lake Vostok isn't alone. In 2005, they found an island in the middle of the lake. Then, two smaller lakes joined the party. They suspect that a secret network of subglacial rivers might link these lakes. Now, very far away from Antarctica, in Venezuela, Catatumbo lightning presents a sinister light show at the junction of the Catatumbo River and Lake Maracaibo. This unsettling lightning phenomenon happens at about 140 to 160 nights a year, going on for 10 hours a day, and can flash up to 280 times in a single hour. The frequency of this lightning show changes with the seasons and from year to year. There was a break between January to March in 2010, causing a bit of worry that it might vanish forever. As the sun sets, winds from the east start picking up speed. The strong wind is called a nocturnal low-level jet, like what you see in the Great Plains of North America. These winds bring moisture, mostly from the Caribbean and the lake itself. This humid air hits high mountain ridges, causing thunderstorms to form over the mountains. Thanks to the ongoing wind situation, more thunderstorms appear as the night goes on. This pattern repeats itself, and is why this area has the highest annual lightning rate globally. The next place scientists cannot explain is in China. That is the Longyu Caves. They have lofty slanted roofs and sturdy pillars. The spot remained hidden for centuries. These human-made caverns, built around 2,000 years ago, decided to reveal themselves only in the 90s. Local farmers drained some ponds and unveiled 5 massive caverns. Further digging exposed an additional 19 smaller caves. They range from 60 to 110 feet in width and 26 to 50 feet in height. Archaeologists found historical relics from the reign of Emperor Zhuan of Han, dating back to over 2,000 years ago. Now, how did these caves survive for more than 2 millennia without falling apart? No ancient records explain the way they were crafted either. The walls show chisel marks, hinting at some layer-by-layer chiseling action, but the exact construction process is still a head-scratcher.
We are up for a crazy Atlantic hurricane season. It may be even worse than that of 2005, the year that brought us Hurricane Katrina. That one took 1,392 lives and cost the country over $100 billion. Experts predict there will be between 17 to 25 total named storms. Some of these storms are about to become hurricanes, with winds reaching over 100 miles per hour or higher. We're already seeing storms sweep across the country, bringing dangers like tornadoes, flooding, and hail. You gotta thank the El Niño Southern Oscillation, or ENSO, for this. This complicated term has to do with El Niño and La Niña, the two giant forces that basically shape our world. Normally, winds in the Pacific Ocean blow west along the equator, moving warm water from South America towards Asia. This warm water is replaced by cold water rising from the depths of the Pacific. But during El Niño and La Niña, this usual pattern is messed up. El Niño is the warm phase of the ENSO cycle. During El Niño, the equatorial winds weaken, causing warm water to shift back towards the west coast of the Americas. This means less cold water rises to the surface. The weather in northern parts of the US and Canada become drier and warmer because of it. But there are wetter conditions in southern states. In the Atlantic, El Niño weakens hurricane seasons, and it ramps up hurricane activity in the central and eastern Pacific. In Africa, it brings more rain to East Africa but less to southern Africa, West Africa, and parts of the Sahara. La Niña is the cold phase of the ENSO cycle. During this phase, the westward winds along the equator in the Pacific are stronger than usual, and they push more warm water towards Asia. And because of it, colder, nutrient-rich water rises to the surface along the Americas' west coast. These colder Pacific waters push the jet stream northward, giving us drier weather in the southern US, but wetter and colder conditions in the Pacific Northwest and Canada. La Niña also brings warmer winters to the southern US and cooler than normal temperatures to the north. La Niña usually calms hurricane activity in the Pacific, but intensifies it in the Atlantic. In 2023, El Niño was in charge, and it took most storms up before they got to the US. But this year, we've switched to La Niña, and this lady brings us colder water in the Pacific and a pattern that lets storms move a little farther west and reach the Caribbean. And when they get there, they can easily move into the Gulf and affect Florida and other states. The upcoming intense Atlantic hurricane season also has to do with a strong monsoon season in West Africa. It creates moisture and waves off Africa's coast and can travel along the Atlantic and spur hurricanes. The Atlantic hurricane season runs from the 1st of June to the 30th of November, and most activity happens between mid-August and mid-October. Since the 1950s, tropical cyclones have been given names to make it easier for meteorologists to inform the public about them. You're more likely to remember that Leslie is coming than Hurricane X34D is on the way, right? So there are 20 names on the alphabetical list this year, from Alberto to Beryl to Valerie and William. Let's hope it won't get as terrible as the Galveston hurricane. The most fatal natural disaster in U.S. history hit Texas in the year 1900. A Category 4 hurricane smashed into Galveston, demolishing over 3,600 buildings with winds over 135 miles per hour. It took the lives of between 6,000 and 12,000 people. One of the reasons it became so fatal was poor communication policy. Days before the disaster, it was clear to a professional weather forecaster that the storm was moving west. But the Weather Bureau in Washington predicted it would go over Florida and up to New England, which was way off. The Bureau was just 10 years old then, so hurricane science in the US wasn't very advanced. Cuban scientists were excellent at tracking storms because their region is so prone to them. So they knew it was heading towards the Gulf of Mexico. Unfortunately, the director of the Weather Bureau was so jealous that the Cuban forecasters were better than the American ones that he cut off the flow of information from Cuba and made it difficult for local forecasters to issue warnings without going through Washington. In the days before the storm hit, the chief observer in Galveston began to suspect that Washington's forecast was wrong and tried to warn the city, but it was too late. The hurricane left Galveston in ruins. After this hurricane, the Weather Bureau started improving communication, both internationally and within the U.S. The officials in charge are doing everything possible to improve forecasts, support the people, and help the affected areas recover more easily after the hurricanes hit. They're going to try new forecast models to predict tropical cyclones getting stronger, help emergency and water managers prepare for potential flooding, and protect people and infrastructure. Coastal weather buoys in the tropical Western Atlantic and Caribbean have been upgraded, and new drifters and sail drones, underwater gliders, and a lightweight drop sonde will provide real-time data. There are also some things you can do to ensure your safety before, during, and after a hurricane. If you live in a hurricane-prone area, Florida, Georgia, and the Carolinas, you must always be prepared before the high storm season. Make up a family disaster plan that will outline your actions during an emergency. Map out several evacuation routes in case your primary one is blocked, and decide on a meeting place if you get separated. You can arrange drills to teach family members how to shut off water, gas, and electricity, and even make sure the youngest knows how to call emergency services. Pack a disaster kit that will be ready to go at a moment's notice. It should include essentials like food, water, a first aid kit, and flashlights to last at least 72 hours on your own. You can buy a generator to make sure you have electricity in case of a power outage until the power returns. Keep it in a secure place, away from rain and rising water, with proper ventilation. You're also going to need self-powered radios and flashlights. If you can, add a safe room to your house that's strengthened to withstand high winds with reinforced concrete ceiling, floor, and walls. Make sure you have enough canned and non-perishable food and bottled water for at least 3 days. When the storm is about to hit, head north to get away from it, where it will be much weaker by the time it gets there. It's much safer to keep your family and pets together away from the storm than trying to ride it out at home. Try to go in one car if possible. Always follow local evacuation orders, especially if you're in a mobile home. Fill up your gas tank and give yourself plenty of time to get out. Never leave your pets behind. Debris, floodwaters, or flying objects can be dangerous for them. If you're staying put during a storm, you need a safe spot for you, your family, and your pets. This place shouldn't have any windows or skylights. If you're hiding at home, close all interior doors and secure the exterior ones. Quickly find an interior room with strong walls and no windows, like a bathroom or closet. If your home isn't safe, look for a community shelter. Get to your shelter at least 2 hours before the storm hits so it doesn't catch you outside. Bring a battery-powered radio with extra batteries for updates every 15 to 30 minutes. Never leave your shelter even if it seems calm, as conditions can get worse quickly, especially if you're in the eye of the storm. For extra protection, lie on the floor under something sturdy like a table. Don't use electric appliances, phones, or showers during the storm. Don't leave your shelter until you get the official all clear from the authorities. Be careful. There will be many hazards outside.
Asteroid strikes, gamma-ray bursts, supernovae blasts, and other terrifying threats could potentially take out humanity. But one of them is inescapable, a cataclysmic event that will happen around 1 billion years from now and most likely rob our planet of its oxygen, effectively wiping out all life forms. Nearly 2.5 billion years ago, there was a period called the Great Oxidation Event. It gave us a breathable atmosphere, thanks to which we're all alive today. Cyanobacteria, also known as blue-green algae, appeared on Earth, filling the atmosphere with oxygen. It eventually led to the appearance of a world filled with multicellular life forms. But then, one of Earth's greatest die-offs occurred. It happened 450 million years ago. This event is known as the Late Ordovician Mass Extinction. Scientists think it might have happened because the inverse process took place. The level of oxygen on the planet dropped dramatically, and it lasted for several millions of years. It's unclear what could have caused such an extreme event. During this period, the continents formed one jumbled mass called Gondwana. Most life on Earth lived in the oceans, but plants were starting to colonize land. Near the end of the Ordovician period, a climate shift covered the supercontinent with glaciers. This dramatic cooling alone was enough to lead a lot of species to the brink of extinction. And then, oxygen levels plummeted, which caused the second wave of extinction. Scientists have found evidence of this event in seafloor samples gathered from all over the world. Some are sure that glaciers were responsible for changing the layers of the oceans, which had previously had unique temperatures and specific concentrations of elements like oxygen. However, the exact cause of the oxygen drop is still unclear. Whatever the cause, more than 80% of life on Earth disappeared during the Late Ordovician mass extinction. Could a deoxygenation event happen again? Some researchers draw an eerie comparison to today's situation. They say that climate change is already reducing oxygen levels in our oceans. It's likely to make loads of species go extinct and the world to change beyond recognition. Now, even if global cooling triggered the Late Ordovician mass extinction, what sparked this process in the first place? There's a theory claiming it could have been a gamma-ray burst. These bursts seem to be the most violent and energetic explosions in space, and they might be related to supernovae. Thankfully, we haven't seen such a burst close enough to fully figure out what it is. So far, they have only been spotted in other galaxies. If a gamma-ray burst occurred in our home Milky Way galaxy, it could also lead to a mass extinction on Earth. A burst pointed in our direction might only last 10 seconds or so. And still, it would destroy at least 50% of Earth's ozone layer. Yes, in such a short period of time. Even a relatively small amount of ozone depletion is enough to cause serious harm to our planet's natural sunscreen. And wiping out ozone on a large scale can wreak havoc, finishing huge numbers of species, starting with the ones living in the upper levels of the ocean. Gamma rays also break apart atmospheric oxygen and nitrogen. These gases turn into nitrogen dioxide, commonly known as smog. If this smog blanketed Earth, it would block out sunshine and trigger a global ice age. But our ultimate fate is much more dramatic than any of these scenarios. Most life on Earth will eventually disappear due to lack of oxygen after solar activity causes atmospheric oxygen to drop back down to the level it had been before the Great Oxidation Event occurred. The sun ages and puts out more and more energy. At one point, around 1 billion years from now, Earth will reach the point where atmospheric carbon dioxide will begin to break down. That's when oxygen-producing plants and organisms will disappear. Earth won't have enough life forms to sustain the oxygen-rich atmosphere all living beings on our planet need. This process may take as few as 10,000 years, and it seems to be unavoidable. Luckily, we still have around 1 billion years to figure out how to save ourselves.